Welcome to today's lesson. We're going to take a look at macromolecules. So we're going to start with the introduction. Then when we're done with the introduction, we're going to take a look at carbon for a reason that it forms different types of macromolecules. Then we'll also take a look at another substance called silicon dioxide, which is also a macromolecule which is worth studying in this syllabus. So for us to understand macromolecules, we first have to appreciate what are called simple molecular structures. Covalent substances with simple molecular structures consist of small discrete molecules that are held together by weak intermolecular forces of attraction. So we learned about the difference between covalent bonds and ionic bonds, and we learned that covalent bonds have lower melting and boiling points. So covalent bonds that have got simple molecular structures have this property, which is low boiling and melting points, like we learned. So these compounds are held together by these weak intermolecular forces of attraction, which are called van der Waals forces of attraction. So if you see the word van der Waals forces of attraction, you just have to know that these are the weak intermolecular forces of attraction that hold covalent substances with simple molecular structures together. Because of this, covalent compounds, like I said, have low melting and boiling points. So we learned about this, but it's not always that covalent compounds have low melting and boiling points. Sometimes they can have very high melting and boiling points. So in such cases, the molecular structures of such compounds are not simple molecular structures. They are macromolecules. So macromolecules are defined as macromolecules are covalent compounds with giant molecular structures consisting of an extensive network of atoms held together by covalent bonds. These macromolecules have high melting and boiling points despite of being made of covalent bonds. Why is it so? This is because a lot of energy is required to overcome the strong covalent bonds holding the atoms together. So macromolecules have many atoms that have lots of bonds in between them. So despite the covalent bonds being inherent weak, when you need to break these bonds, since they are many, you need a lot of energy to break all of them. That's why they have a high melting and high boiling points. We're going to take a look at what are called allotropes. So most macromolecules, or should I say some of the macromolecules, exist in what are called allotropes. So what are allotropes? Allotropes are same elements in different physical forms but in the same state. So allotropes are same elements. So for example, it can be carbon, so you can have two carbons which are same elements but they are in different physical forms. So you can have one carbon and another carbon. They are all carbons but they are in different physical forms but in the same state. They can all be solids, but they don't look the same, even though they are solids and they are all carbon. Such elements are said to be allotropes. Each of the elements is an allotrope of the other, or of the original element. So allotropy is the existence of an element in different physical forms but in the same state. So in the example that I gave, carbon, since carbon has two forms, like I illustrated, you can say that carbon has the property of allotropy, meaning that it exists in more than one physical form but in the same state. So in reality, carbon exists in three forms, but in this syllabus we're going to take a look at two forms. So the first form of carbon is called graphite, the second is called diamond, and the third is called amorphous carbon. But we're going to take a look at graphite and diamond. Amorphous carbon is a little bit debatable because when we go to the definition, it says same state, but amorphous carbon, amorphous, the word, it means something that exists between, or that has a form which is like a solid and also like a liquid, like porridge. So porridge, it's a bit a solid and a bit a liquid. So such a thing is called an amorphous substance. So the third allotrope of carbon, amorphous carbon, don't worry about it. It's not that much emphasized in the syllabus. We're going to concentrate on graphite and diamond. So we're going to start the structure of graphite, the physical properties of graphite, and the uses of graphite. When we are done, we also move to diamond. So graphite is a soft, black, crystalline form of carbon that is a fair conductor of electricity. So there's something interesting here. Most covalent compounds, as we know, they are not conductors of electricity. They do not conduct electricity because they don't have charged ions or free electrons. For that, they do not conduct electricity. But graphite is the only macromolecule or the only covalent compound that is able to conduct electricity to some extent, due to a reason that we are going to explore soon. Graphite is made up of flat sheets of carbon atoms, as you are going to see in its molecular structure. So this is the molecular structure of graphite. So there may be 2 or 3 things to notice. The first is, by the way, the black things here represent carbon atoms, and these ones, as we learned, are covalent bonds. So if you look at this carbon atom, it is connected to 3 other carbon atoms, this one, and this one. And if you look at this one, it is also connected to 3, this one also to 3, this one is connected to 3. Of course, the third carbon atom which this is connected to cannot be seen here because we are just analyzing a part of the entire structure. So it is connected to this one, and another one which we can't see because we're just analyzing just a part of the entire graphite structure. So each carbon atom is connected to 3 other carbon atoms, and they form a ring of 6 atoms. So they form rings like this: 1, 2, 3, 4, 5, 6. So there are 6 atoms in each ring, which is connected to another ring with 6 atoms. And on the bottom, there are also the same rings of 6 atoms. So graphite, at the end of the day, the top part here is like a single sheet or a plane of atoms, and the second one is the same. So it has got these sheets of atoms. Another thing that we need to learn about graphite, which of course is going to explain why it's a very good conductor of electricity, is this carbon atom is connected to 3 other atoms. But remember, the valence electrons for carbon is 4. In short, it needs 4 more electrons to form a bond. So the valence electrons, which are 4, is going to share 1 with this one, which is also going to contribute 1, and it will remain with 3. It is also going to share another one with this one, and it will remain with 2. It is also going to share another one with this one, and it will remain with 1. Where is the 1 electron going to be? It's going to be delocalized. It will be moving about since it is not bonding to anything. So all these are going to contribute, or are going to have 1 electron which is delocalized. Remember, just like in metallic bonds, delocalized electrons are responsible for conduction of electricity. So these delocalized electrons are going to be able to conduct electricity, giving graphite this property here, fair conductor of electricity. So let's take a look at some properties of graphite. But before we can do that, here is how graphite actually looks like. This is graphite. All of us have seen graphite in our lives, as you are going to understand soon. So here are some physical properties of graphite. Number one, it is a good conductor of electricity because of free moving electrons in between the layers of carbon atoms. 2. It is soft and slippery. This is because the sheets of atoms can slide over each other easily. 3. It writes well on paper. It writes well on paper. So in short, graphite is the lead of pencils that we use for writing. So all of us have seen graphite before. 4. It has a high melting point. Actually, this was supposed to be number 4. I don't know why I labeled it as number 5. And this is the actual number 5. Sorry, this is number 4. Sorry, my numbering here is messed up. This is number 4. So it has a high melting point. The reason is because the strong bonds between the carbon atoms within a layer make graphite difficult to pull apart in the direction of the layers. So what this point is trying to say is, if you take a look at each of the layers, there are many bonds there. So to break those bonds, it needs a lot of energy. But the bonds between the layers, between the sheets, they are very weak. But within a sheet or within a layer, you need a lot of energy. Therefore, this gives graphite a high melting point. Here are some uses of graphite. First, it is used as a lubricant because the layer of carbon atoms slide over each other easily. 2. It is used as an electrode in electrolysis. So we're going to start a process called electrolysis, and it's just a process of breaking water apart into hydrogen and oxygen. So in that process, we use graphite as an electrode. 3. It is used in making the lead for pencils. This is because it leaves a gray streak when it is drawn across a sheet of paper. We move to diamond. Diamond is a colourless crystalline solid with an extremely high density. Each carbon atom shares electron with each of its 4 nearest neighbors, thus forming 4 covalent bonds. So this is what differentiates diamond from graphite. Diamond shares all of its 4 electrons to other the carbon in diamond shares all of its 4 electrons to other carbon atoms, unlike graphite, which only shares 3 electrons. Here is structure of graphite. So each of the carbon atom in graphite, it is connected to 4 electrons, unlike graphite, which is connected to 3 electrons. So this is the structure of graphite. I don't expect you to master this, or in short, you're not expected to master this, but you should be able to tell the difference between this structure and that of graphite. If you have been given that of graphite, you should be able to tell this is for graphite and this is for diamond. And the clues that you can use are simple. 1, in diamond, 1 carbon connected to 4. Well, in graphite, 1 carbon connected to 3. In graphite, the atoms form layers. Well, in diamond, they do not. So this is diamond. This is how it looks, different from graphite. Here are physical properties of diamond. The first is it is very hard. It is actually the hardest substance known. Secondly, it has a very high melting point because each atom is held in place by 4 strong bonds. So diamond has got a higher melting point than graphite because each atom has 4 bonds surrounding it, unlike in graphite where there are only 3 bonds. It is colorless and transparent with a dazzling brilliant luster. It does not conduct electricity because there are no ions or free electrons in it to carry charge. Here are some uses of diamond. First, it is used as material for cutting tools and drilling devices. So diamond is very strong. Therefore, it is used for cutting tools and drilling devices. How so? Since it is the hardest, therefore it can penetrate through anything. It is used for cutting glass. So if the materials that are used to cut glass are made out of diamond. Finally, we take a look at another macromolecule called silicon dioxide. So its chemical formula is CO2, which simply means in silicon dioxide, the element silicon is bonded to 2 oxygen atoms. You can even imagine this to be something simple like one silicon with 2 oxygen atoms, but it has a behavior of carbon which allows it to form many bonds with itself, therefore making resulting in it being a macromolecule. So it is mainly found in sand and commonly called silica. So the sand that we know is made of silicon dioxide. It is formed when silicon reacts with oxygen, as you can see from the chemical formula. Here are some characteristics of silicon dioxide. We're not going to take a look at its structure, but here are some characteristics. And what is common between silicon dioxide and graphite, diamond, is silicon dioxide has the same behavior as carbon of forming many bonds with different elements, therefore resulting in it being part or forming what are called macromolecules. So that's the many similarity. Maybe it did not come out clear, so let me just summarize it. So the many similarity between silicon dioxide and carbon or graphite and diamond is it forms a macromolecule. So here are some characteristics of silicon dioxide. One, it has a high melting point and boiling point, and it does not conduct electricity. Here are some uses of silicon dioxide. It is used in making glass. So the glass that we use for making windows, it is made out of silicon dioxide. It is used in fire extinguisher. It is used in iron extraction. So later we're going to learn about how iron is extracted. So silicon dioxide is used in the process of extracting iron from its ore. So when miners get the ore that contains iron, to extract that iron they use silicon dioxide. It is used in the making of ceramics. You know, ceramics are made from sand, so that's where this is coming from. Silicon dioxide, which is sand, is used in making of ceramics. So this marks the end of this topic, macromolecules. So this has no formulas, no skills. It's all about just understanding macromolecules. Hope you have enjoyed. Happy solving.